Okay, so hello to everyone, and thank you to be here with Machine Learning Together Milan. As I said, this is the first year of Machine Learning Together Milan, so it's a very good thing to start with this conference, with these lectures. About what? About classification, in particular, unbalanced classification. So we have already started with a series of conferences about classification with balanced classification. And now we will start with another type of classification, the unbalanced one. So this is the today topic, but let me say something about Machine Learning Together Milan. This is a group of different people, like as you have seen, as with Andrea Megaro, Giovanna, Han, and some others, Marcos, and some others ones. And we study together some problems, some typical and important topics about machine learning, and we try to expose, to share our knowledge about these topics. So today we will start. We will try this new topic, and we will see for 4 lectures, so for meetups, this topic. The first 2 ones, they will be theoretical, and the two other ones will be practical. So we will see the theory at the beginning and the practice at the end of these meetups. After that, we will see with Andrea Megaro a new topic about unsupervised learning in time series. So we have different topics, and these meetups are open to everyone. So if you are interested in and you want to present some of the topic that you like, that you love, that you want to expose to other people, you can participate and expose your topic. So we will start. Okay, I don't see where is the share. Okay, share screen. Okay, so now I take my my slides. I will start to present what we will do. Okay, share the screen. Okay, are you seeing?
Yes.
Yes, sure.
Yes.
Okay, so the topic, as I said, is unbalanced binary classification. So what we will do today, so not today, in these meetups, in the theoretical part, we will see an introduction to the unbalanced binary problem, because we have to understand why they are so important in the real world, because they are very, very important. We will see why. And I think that a lot of you are seeing this topic because they have already seen this problem in their jobs, or they are studying this problem in general. After, we will try to see, to do a brief mathematical recap on the classification, only to better understand the mathematical formulation of the problem of classification. After, we will see what will be the theoretical problem that will be useful to understand the different techniques to solve to try to solve the unbalanced problem. So we will have a benchmark, something like that, and we will expose the different techniques, the different supervised method for the unbalanced classification. So here we can see some of these techniques, the metrics that we can use, the threshold selection method, the sampling methods, the cost-sensitive training. And at the end, you can find a bibliography about this topic. So if you are interested to understand, if you're interested in this topic and you want to understand something more, you can read this bibliography, and you can read something else. Okay? So let's begin with a definition of, let's begin with a definition of unbalanced binary classification problem. So it's a binary classification problem. So we have an outcome. We have two possible outcomes. And the target output can be two classes. And in particular, we are not in a balanced problem, but we are in an unbalanced one. So one of the two classes is more frequent than the other one. Okay, so we can see an example. We have this bar plot. We have the class 1 and class 2. And as you can, the bar plot represent the number of sample in each class. So in the class 1, we have a lot of sample. And in the other class, we have very few sample. And it's a very common in real data set. Why? Because it's very difficult to have a balanced binary problem, because it's very difficult to have a 50-50 frequency in each class. So it's more common that you have a certain sort of imbalance. So if you have, I don't know, 0.4 as a proportion, you have 0.4 of the class 1 and 0.6 of the second class. Okay, it's not perfectly balanced, but it's quite balanced. So it's not very imbalanced. But a very strong sort of imbalance is when you have I don't know, maybe 0.1% of the sample of the class 2 and 0.9 of percent. No, 0.9. No, it's 0.9, and it's enough of the entire data set. So it's a problem of frequency of the samples in each class. So, and what are two important examples that you can find in the literature? For example, the first one is the fraud detection. For example, we are a bank, and we can have two kind of people, the fraudulent one and the honest ones, okay? And usually, but maybe, I don't know, it depends on the context, but usually the fraudulent one are less frequent than the honest one. So it's more difficult to understand what are the people that are fraudulent and what are the honest. The other type of another classical example of fraud detection of unbalanced classification is the call advertising. In this case, we are a call center. Okay, we want to sell a product, and for doing it, we have to contact the people. And what is the problem? The problem is that usually a lot of people doesn't answer to the call. So you have to understand what are the people that will answer to the call, and with a high probability will buy the product. So as you know, it's a very unbalanced problem. And what are the problems associated with the classical approach, with the classical algorithms? For example, I don't know, I use classical random forest, classical logistic regression. What are the problems? The problem is that these algorithms are built under the assumption that we have the same number of sample in each class. Okay, and we will see later why. So, but is the first point. And the other point is that the classical metrics to optimize the models are based on the fact that they focus on the majority class. And okay, I will explain later in more details what I want to say with these two problems, okay? what I want to say to introduce the unbalanced binary problem is that there are different approaches, okay? There are a lot of approaches. For example, supervised approach with threshold moving sampling approach, anomaly detection, some other ones, okay? Unsupervised approach with isolation forest and a lot of other ones, okay? So there is a very big literature about this problem, but we will see only a small part in the supervised field, because it's the more common in general, and it's also the most useful and the easiest ones to use in general. So I think that now it's quite clear the context. So what we are seeing, what we will see in the next slides. So let's try to do a brief mathematical recap on classification. If you have studied a little bit about machine learning, you know that classification is a supervised machine learning problem. So supervised, when we talk about supervised, we have an output, we have an input, and we have to find the relationship between the input and the output. So in general, we have an output y that is a class because it's a classification problem. And what we want to estimate is the probability of a sample to be of a certain class. Okay, so what we have is an input x, sorry. And we have an output y, but we don't want to estimate y, but a probability associated to y, okay? And we know that we want to understand what is the relationship between x and y, so x and the probability of y. And we know that the reality has also a source of error, an error source, that we will call epsilon. Okay, so in this equation, we have that our estimated probability will be written as f of x plus epsilon, that is the error term. But we will talk about binary classification. Okay, so we have only two classes. Okay, two classes, what we call a positive class and a negative class. The positive class, as you know, due to the fact that we only have two classes and the probabilities sum up to 1, we know that we have a class associated with a probability p, and the other class is associated with 1 minus p. So it will be interesting to study only the probability p, because if we know p, we only know 1 minus p. So we will be interested in the positive. We will talk about positive class when we talk about the probability associated to the, sorry, we will talk about positive class, okay, when we talk about the class associated with the probability p. The negative class will be associated with 1 minus p. Okay, so this is the very important terminology. And we will talk about the positive class when we will talk about an event of interest. Okay, so in the case of fraud detection, when we want to find the probability of a fraudulent person, we say, okay, the fraudulent person belongs to the positive class. Okay, so this is the negative class. Okay, and as you know, how can we classify the samples using the probability? We select a threshold. Okay, so we have maybe we say, okay, up to 0.5 or 50%. Okay, up to 50%, we can say, okay, this is of the positive. It is a sample that belongs to the positive class, or if we have a probability that is less than 50%, we can say, okay, this sample belongs to the negative class. So okay, so this is clear, okay? So this is the threshold, the rollout of the threshold. Usually, when we talk about balanced classification, we have a threshold of 0.5, okay? But we will see that when we talk about unbalanced classification, we will not talk about, we will not use a threshold of 0.5. We will use a different threshold. So let's remind this fact because it's very important. The threshold depends on the problem. We only have a probability, but the threshold depends on, we have a probability associated to the problem, but we will change, maybe we will change the threshold. And so, okay, we have seen okay, admit, hello Ale. So we have seen that we can use the threshold to select the labels, so we can decide if you are of you belongs to the positive class or the negative one, and maybe what are the possible results? In what sense? We know that our algorithm predict a certain result, but maybe the real class of the sample is another one. So maybe you predict that your sample belongs to the positive class, but maybe you the real class is the negative one. So you can write predict, you can do some mistakes, and so you're interested in when you're doing mistakes, what are you doing, and when you are doing something right, what is this right prediction? What are these right predictions? So in practice, what I want to say is we can use what we call a confusion matrix. Okay, so these in a binary classification problem is a matrix of 4 possibilities. For example, we have in this case, because sometimes they are switched, we have on the rows, we have the predicted events. On the columns, we have the real one. So in this case, it's predicted vs observed. And event in this case, event stays for positive, and non-event stays for negative. So if you predict right, you predict positive and the observed, so the real one is positive, you have a true positive. If you predict positive but the real class is negative, you have a false positive. If you predict negative but it's positive, you have a false negative, and if you predict negative and you have observed a negative, you have a true negative. So you only have 4 possibilities. And we can create different metrics with this confusion matrix, okay? So the first one is the accuracy rate. This is the classical one. So this is the usual metrics that you use at the beginning in machine learning. So you are saying, okay, I have true positive plus true negative against all the possible samples that we can have. So it is what we have done right. But it's not the only possibility, because we have also the sensitivity that we can also call recall, that is defined as a true positive against all the positives. So all the true positive plus the false negatives. So the false negatives are in reality positive, but we have predicted them as negative. But in reality, they are positive. So true positive against all the positive samples. Specificity is the same, but for the negative class. So true negative against all the negative samples. And the precision is something similar, but different. In what sense? In the sense that we have true positive against what we have predicted as positive. So it's similar to the sensitivity, but where in the sensitivity we have the true positive against what is really positive. In the precision what is predicted as positive. Let's see what problem we will use to explore the unbalanced classification problem. We will deal with the two-class SIM dataset of the current package in R. In this case, this is a very toy problem. You can select the degree of noise that you have in this dataset. You can select so how many sample you want of the first and the second class. In this case, I've chosen the 90.52% of the first class and the 0.48% of the second one. Okay, and so you can see in this projection or in 2D this dataset. So let's see this chart. Let's focus on this chart, and as you can see, you have very few blue points on the border, and a very big concentration of red points. Okay, so as you can see, is a very different problem with respect to the other ones that we usually solve. So it's you can see from this plot what we are dealing with. Okay, I think it's quite clear the problem. So what we usually do when we try to solve this classification problem? Okay, we take our different models. We take a random forest. We take a logistic regression. Maybe we take a neural network. We try to learn something, okay? And in the end, we select the metric, like, for example, the accuracy. And we say, okay, let's take the model with the best accuracy. Okay. Let's try to do it. For example, let's take a random forest, a logistic regression, and a KNN, and compute the accuracy. As you can see, the accuracy is near to 100%. But if we see the sensitivity in particular for the logistic regression, and in particular for the KNN, is very low. And the specificity, on the contrary, is very high. What is the reason? The reason we will see that is because if we take naive models that predict all the sample as negative, this model has an accuracy in average of 99%. Because if we take our sample, we have more than 99% of the sample that comes from the negative class. Okay, so a naive model that predicts so that all the sample as negative, this is a no information model. We don't have learned anything from the data. We're only predicting all the samples as negative. So in this case, what is the reason? Because the positive class is not important. Let's come back to the accuracy definition. As you can see, if we are dealing with an unbalanced classification problem, the magnitude of the different of true positive and true negative, and in general of the negative and the positive class are very different. So in the end, the true positive are not very important for the accuracy rate computation. So it's like we are only using the negative class to compute this metric. So this is the reason, because there is no differences between a naive model, and another model like the KNN, because in this case, they are predicting exactly the same thing. So, as you can see, we have a problem. So we have to do something. And what we are also seeing is that this model are focusing on a negative class. Ale, togli l'audio. Okay, but the problem is, okay, maybe sometimes we are interested only in the negative class. Okay, so we can say, okay, it's not a problem. We can use the classical algorithms in such a way. So it's not a problem. We can do we can do nothing. I mean, we can say, okay, it's fine. And so these algorithms are what we want. But in general, if we are working on the unbalanced problems, it's because we don't want to use the algorithm in such a way. But maybe if we say, okay, let's focus only now on the positive class, maybe we will neglect the negative one. So maybe it's not the result that we want. So sometimes, and in the most of the times, we're interested in a trade-off of them. And the different techniques that we will use depends on the problem. So what trade-off what is the trade-off that we want? So the trade-off will depend on the problem. So let's go into the supervised method for unbalanced classification. So as we have seen what we can do in general to learn from an unbalanced data set. We can do nothing, cross our fingers and say, maybe we can obtain a good result. As you can see, the random forest has a sensitivity of 0.26. Maybe sometime it's a good result. Okay? But we can change the classification metric, because maybe we can change it, we can optimize with respect to the sensitivity and not the accuracy. And we will see in more detail what I want to say with that. We can change the threshold cutoff to classify, because we are using a threshold of 0.5, and maybe it's not the best that we can do. We can use sampling methods. We will see what I want to say with sampling methods. But the last thing that we can do is weight the loss, because all the machine learning algorithms will use a loss to penalize the errors. But the usual loss are penalizing the two classes in the same way. But maybe it's better to penalize some class over another one. Some class more with respect to another one. Okay, let's try with the first method, the classification metric method. So in this case, we say that the first metrics that we can use is the accuracy metric. But we have said that this metrics is too much oriented to the most frequent one. Okay, so we have a difference because the difference of order of magnitude. So the solution is maybe, I don't know, optimize with respect to the sensitivity, the precision, but also with respect to the AUC of the ROC curve and AUC of the precision recall curve. And we will see these two curves now. Let's try to build the ROC curve. In this case, the ROC curve is a curve, okay? This is quite clear, but we have on the x-axis 1 minus the specificity. The specificity is, as you can see, the true negative against all the real negatives, okay? And we have the sensitivity on the y-axis. So let's see this formula some seconds. We have 1 minus specificity against sensitivity. And 1 minus specificity is what we call false positive rates. So how many errors we are doing in the positive class with respect to all the negative. So what are the real negative that we predict as positive with respect to all the negative, all the negative ones. So as I said, yes.
You said that the false positive over the own negative, but I see that Tn plus Fp. How can it should be Tn plus Fn, right? Like
No,
false negative.
No, it's false positive because what I said is a specificity is focused on real negatives, non-predicted as negative. So the true negative are predicted as negative, and the real label is negative. So true negative. False positive are in reality negative, but predicted as positive. Okay, is it clear?
Yeah, it's clear. Thank you.
Okay, but what I said at the beginning, I say that we usually with a machine learning algorithm, we don't predict the label, we predict the probability, and after using a threshold, we predict a label. So what we can do is to see what it changes when you change the threshold and what it changes in the label. So in what sense? Okay, I use the probability, I change the threshold. Changing the threshold, I change the true positive, the false positive, the true negative, and the false negatives. Okay? And so if I change these 4 quantities, I will also change the confusion matrix. And if I change the confusion matrix, I also change the sensitivity and the specificity, and so also the 1 minus specificity. So in the ROC curve, we are capturing this thing. So we want to see how the sensitivity and the false positive rate change according to the threshold change. So let's try to see on the top. If we start from the top right, we start with a threshold of 0. Okay, we have a threshold of 0. We are predicting all the samples as positive. So the sensitivity is 1 because we have predicted all as positive, but also the false positive rate is 1 because we have also all the samples associated to the negative class are predicted as positive. So we are on the top right of the curve. If we increase, the threshold, as you can see in green, we have the threshold of 0.3, and and if we increase the threshold on to 0.5, we are approaching the center of this graph. Okay, so the 0 in the false positive rate and the 0 in the sensitivity. So if we increase the threshold, we will reduce the number of positives. So we will reduce the sensitivity, but we will also reduce the number of false positives. So also the 1 minus specificity. So you have to see this curve in what sense? In the sense that we will start at the top right, and increasing the threshold, we will go to the down left, to the bottom left, and the diagonal is the random classifier.
Sorry, can I ask a question?
Yes.
The threshold in case of logistic regression, right? In case of random forest or neural network, there is no threshold, right?
No, we have a threshold in all the machine learning models. For example, if you think about a random forest, you're talking about a tree, and in the tree, how do you predict the probability? You have in each node a certain number of samples of one class and a certain number of neighbors of one other class. Okay, and so you can count the number of sample of the positive class, and you can divide by the number of the other class, and you obtain in such a way the probability to belong to the positive class. This is the usual way to predict the probability with a tree, and so with a random forest. And you can do the same thing in a neural network using the exponential, the exponential. I don't remember the right term. Exponential weight. I don't remember. So the classical method is you create an exponential and you divide it by the sum of all possible exponential. I don't remember the name. The softmax, exactly. And so you obtain a probability, also in this case. So all the classification algorithms use a probability. And so for all the classification algorithms, you can create a ROC curve. Is it clear?
Yes, thank you.
So,
thank you.
I cannot prove now why the bisector is the random guessing, but you can do it using the classical probability. It's quite easy. And on the contrary, the perfect classifier has a ROC of with an equation like epsilon equal to 1. What is the reason? Because with if y equal to 1, we are talking about a sensitivity equal to 1. If we have sensitivity equal to 1, whatever is the false positive rate, the reason is because the perfect classifier is classifying perfectly all the positives, all the samples, because sensitivity is always 1, so the false positive is always 0. So this is a perfect classifier. So what we're saying is the perfect model will approach the line y equal to 1. And what we can do in general to select a model is to take the area under the curve. So we can compute the integral of this curve. And the perfect, the best value for the AUC is the area of the line y equal to 1, so 1. So we will try to select the model that approach is ROC is AUC to 1. Okay, this is a classical method. Okay, so the bigger is the AUC, the best is the model. But it's not very true in general, as we will see. But this is the idea. And why it's very important? Why is a good method, the AUC? Because it's threshold sensitive. Because we are not focusing on what is the best threshold for this model. Okay, we are not talking about threshold. We're talking about a probability. We can change the threshold, but if you take the AUC, you can take, it's not a problem of threshold, because you are not taking the threshold. You are only taking the area under the ROC curve. And the other fact is the insensitivity to disparity in each in the class proportion, because we are focusing on the sensitivity and specificity, and the sensitivity is the proportion of positive against all the real positive. So it's a proportion. It's not a, if we have, I don't know, 5 predicted, 5 true positive and 25 positive in general, okay, is the same as I don't know, 25 25 true positive and 125 real positives. It's not a problem of how many positive we have, but the proportion of them. Okay, so it's insensitive to. It's only sensitive to the. It's only sensitive to this proportion. Okay. What are the problems? The problems are that different curves could cross, okay? Because there are no reasons, because we have a perfect, because each model will have its ROC curve, but their ROC curves can differ, can cross, and so in this case we can maybe, I don't know, it's not very easy to understand what is the best curve. We can measure the AUC, but maybe we have some similar results, because we have a ROC curve that is better on some part and another curve that is better on some other parts. Okay. And sometimes the threshold too can be a very important discriminating factor, because as you can see, we can have some, maybe we have a good sensitivity associated to a certain threshold that we cannot reach with another model. Okay, maybe we're interested in a sensitivity around, I don't know, 0.9. And with another model, it's impossible with whatever is the threshold to obtain a sensitivity to 0.9. And sometimes we are interested, maybe we're interested in this kind of sensitivity. So the threshold can be very important. And the last problem is that when we have a very, very unbalanced dataset, this metric is not very reliable. What is the reason? Let's take an example. In this case,
Julian.
Yes.
In this case, you try several thresholds and construct the ROC curves for each one to select the best threshold or the model.
Yes. Okay.
It's an interactive method.
What I said is, okay, the first method can be, I don't know, I use the AUC, okay? And sorry. You construct the ROC curve for all the models and you compare them, okay? And you can use the AUC to compare and to select the best model. But the problem is that sometimes...
but the models are selected, each one with its own threshold, okay?
Yes, exactly. You create the label for each model, so you can obtain the different matrices, the confusion matrices for each model, and so you obtain the respective sensitivity and the false positive rate for each model. Okay.
Okay. Thank you.
And so after that, you obtain different ROC curves and different AUC, and but this curve could be very, very different. So they could cross, and sometimes maybe using a certain threshold, maybe I don't know, you have a better AUC for a model, but if you use a certain threshold, you can obtain, I don't know, as I said before, a better sensitivity that is impossible for the other model. And so you can say, okay, in this case, the threshold is important and you cannot capture with the AUC this fact. But the very, very big problem in general is the third one, because let's take this example. We have a big imbalance with these two classes. You have predicted classes on rows and the reference classes on the right. You have the negative and the positive class. You have these proportions, and you try to compute the sensitivity, the specificity, and the precision. The sensitivity is how, in the end, in the end, how many positive you see. Okay, so your algorithm is very good to find the positive. The precision, what the precision say is how many. Okay, you predict a lot of positive, but how many of them are really positive? Because if we come back, let's come back to the definition. The precision, the sensitivity is the true positive against all the positives. So if we have a good sensitivity, we are seeing all the possible positives. But if we see if we are seeing the precision, we have the true positive against all the predicted as positive. What I want to say is that if we are predicting using, for example, a threshold equal to 0, okay, we have a very good sensitivity because we are seeing all the positive samples. But we have a very, very bad precision because we will predict a lot of false positive. So the precision will be very, very low, but the sensitivity will be very, very high. So in general, we need a certain trade-off between sensitivity and precision. Okay? So let's come back to the slide. So in this case, we have a very good sensitivity, a very good specificity, but a very bad precision. And what is the reason? Because we are predicting a lot of false negative. So in this case, we are not seeing what is the relationship with the ROC curve. We are only seeing that we can have a problem. Sometimes we can have a problem with with unbalanced dataset. In this case, and in this case we have a very big difference between the positive class and the negative ones, because as you can see, the order of magnitude of the negative class is around 10 to 4, and in the other class is 10 to 2. So we have 2 order of magnitude of difference. Okay, so it's very, very different. But and we can see that we have this bad result for precision, but we are not seeing why this is a problem for the ROC curve. So, okay, in this case, let's come back to the definition of false positive rate. The problem is that if we have very few positive, in general, also the predicted as positive will be very, we will not have a very, we will not have a lot of false positives. So, because we don't have in general a lot of positives. So in general, we will see a very big difference between the order of magnitude of false positive and true negatives. Okay, because maybe we have a lot of true negatives, but we will predict very few false positives. And so the problem is that in this case, the false positive rate will be around 0. Okay, and so the problem is that we will have a false positive rate around 0, and it's not important that we have a lot of few false positives, because in this case we always have a false positive rates around 0, and this is not related with a good algorithm, but this is only related with the structure of our dataset. So we will have whatever is the threshold, we will whatever is the algorithm, we will have a false positive rate equal near to 0, a sensitivity that can be whatever we want, but it will be very high, okay, because we can select what sensitivity we want. And in this case, we can have a very, very good recall, very good sensitivity, as we have seen in the previous example. And so we will have a good result for the AUC of the ROC curve, but we will have a low precision. So what we learn from this example is when we have a very big unbalanced problem, a very, very big unbalanced problem, maybe it's better to take into account the precision too. Is it clear, this problem?
Yeah, it's clear. Is it we use the precision rate to
Yes.
calculate the F score, isn't it?
Yes, we will. Now we will move on, and we will try to use the precision too. Exactly. So.
Yeah, I see that it's common to use F score, I think.
Yes, we will see what I want to say. We will see the F score later. Now I will not focus on the different scores. I only want to describe what curve are useful for our problem. We will do it step by step. So now it's clear that the ROC curve is not the best curve in general. We can use it. Okay, it's a very good tool for the unbalanced problem, but no, not when we are doing with an unbalanced problem. So let's move on. Let's try to use another curve, the precision recall curve. In this case, we have on the x-axis the recall, and so the sensitivity, because it's the same. And we have on the y-axis the precision. And in this case, we start from the bottom right with threshold equal to 0. Okay, or in this case too, we are changing the threshold. Okay, like in the ROC curve, and we increase the threshold. So we increase the threshold. So we are if we have a threshold equal to 0, we have all the samples predicted as positive. Okay, but we also have a lot of false positive, so the precision is equal to 0. We increase the threshold, so we can reduce the number of positives, but we are also increasing our precision in the classical sense of the term. So because we are not predicting all the classes as positive, so the result for the precision is better. And in this case too, we can select, we can compute you can create the precision recall curve for each model, okay? And we can compute the AUC for each precision recall curve associated to each model. And we can select the best model according to the best AUC. So in this case too, the best model is the model with y equal to 1, so best precision, best recall, and whatever you want. And as you can see, as I said, in a very unbalanced data set, for example, 1 against 100, it's better to use the precision recall. I can see in this case too. Let's see a numerical example of the previous problem. For example, in this case, I'm using the ROC metric to select a model. In this case, we are using a random forest, and we want to select the number of columns. So what we call mtry, the number of columns used in our in each tree of the random forest. Okay, if you remember the random forest, each tree will have we'll see only a certain number of columns of the dataset, and we can tune the random forest, changing the number of columns used by each tree. So mtry is the number of columns used. We can compute the AUC of the ROC curve here, the sensitivity, the specificity, and the accuracy. The accuracies are quite similar, okay? And as you can see, the ROC curves are very high, but In this case, you can see that the sensitivity in this particular case is not very high. So it's quite particular, because in this case we are seeing that also the sensitivity is not very high. No, sorry. I think there is a no. Sorry. I think it's an error, because it's not sensitivity. I think it's precision. I don't know why I've wrote sensitivity. It's precision. So as you can see, we don't have a very good result for the precision. So I have to change the column name. So as you have seen, we talked about threshold. So we can change the sensitivity and the false positive rate, the precision, if we change the threshold. So if we change the threshold, we can change what are the predicted labels, okay? I think that is the most important fact that we have learned today. So we change the threshold, we change the labels. If we change the labels, we change the sensitivity and blah, blah, blah. And the precision and so on. And if we change the sensitivity, specificity, and precision, we change the ROC curve and the precision recall curve. Okay. And let's suppose that now we have selected our model according to the AUC of the ROC curve, for example. I don't know, it's the same for the precision recall. And we have a model, but we have to decide what is the best threshold for our model. Okay, and what is the simplest idea? The simplest idea is, okay, we know that the best model is y equal to 1, so we can select the point of the curve, so the threshold associated to this point, such that this point is the nearest to the perfect model. So is the point nearest to the 10% of sensitivity and 10%, the 100% of sensitivity and 100% of specificity. So associated to the nearest point associated to the top left corner. And so we choose the associated threshold to this point. Another possibility is to maximize the Yadens J index. So how we define this index? This index depends on the threshold and is the sum of sensitivity plus specificity. And this number can be more than 1. So we subtract 1. So it's a number between 0 and 0. Usually it's a number between 0 and 1, okay? But if sensitivity and specificity, no, it's impossible. No, sorry. It's impossible to have a sensitivity and specificity equal to 0 together. It's impossible. So it's a number between. I think it's possible to prove that it's a number between 0 and 1. So what we want is to maximize this number. So to maximize the trade-off between sensitivity and specificity. Another classical metric is the J-mean. So it's the product between sensitivity and specificity, and we also do the root. Okay, these are three methods that we can use to select the best threshold. So we can try to optimize our algorithm using these three metrics. So let's see. For example, let's try to select a random forest using the problem that we are using. So the 2-class sim problem. We use m_try equal to 13, and let's try to use 3 threshold. The closest top left. Okay. In this case, the Yadens J index returns the same threshold as the closest top left, and it's a very low threshold. But as you can see, the specificity and sensitivity are quite different from the default model with the threshold equal to 0.5. So as you can see, you have lost a little bit of specificity, but you gain a lot of sensitivity. This is not very classical. In general, you don't obtain a gain like that. It's quite impossible. But we are dealing with a very, very simple problem. So in this case, is quite uncommon. But when we do the practical lecture about the practical meetup about that, we will see that there is something. We will see a practical example where the gain is very different. When we are dealing with not a...
Can I ask a question?
Yes, yes.
In a balanced dataset,
Yes.
why I should select 0.5 instead of doing the ROC curve?
Okay, it's a very, very interesting question. And to understand it, you have to understand why we are changing the threshold. Okay, I don't. At the beginning, I thought that I don't want to talk about this fact, but I think it's very important because the threshold. Let's think about the KNN. The KNN. What are you doing in a KNN? You are saying, okay, let's take a sample. Let's see the neighborhood, the neighbors. Okay. And you say, okay, if I have, in a balanced problem, you say, if I have a majority of positive class, I predict this sample as positive. And if I have a majority of negative class, I predict as negative. The problem with the unbalanced dataset is that the majority of your neighbors are negatives. But this does not depend on the real, I don't know, sorry. Let's come back to the first example. It is clear. I think it will be very, very clear. Let's take, for example, if we are on the top right, okay, and you take, I don't know, what point do you prefer in the border, on the verge, for example, between the two classes, okay? So you can see that if you take the classical KNN, the majority of neighbors are red, so are the class 1. But it is not related with the fact that this point is in reality, sorry, it is not related with the fact that the point belongs to the class 1, because for each point in the 2D graphs, the majority of the I don't know how to explain it. It's not easy. The fact is that the majority of the 2-bar plot is composed by points of the class 1 and not of the class 2. And it's very difficult to answer in a very clear way. So if you are in the top right zone, if you take I don't know 10 neighbors, maybe it's a very you obtain 5 blue points. I don't know, but you also obtain 20 red points. Okay, and it's quite clear that if you have these results, you belongs to the class 2 and not to the class 1. But if you use a threshold of 0.5, you will be classified as positive, as class 1. Now, I think this is not a clear way to answer to your question. I will try again to answer to your question. The fact, okay, let's try again. The fact is that when you use a KNN, it's very difficult, of KNN or some other algorithms, it's very difficult to find the minority class. So if you use a threshold of 0.5, whatever is the result, whatever is your location in this plot, you will be predicted with a high probability to belongs to the first class. But it's not related to the fact that you really belongs to the class 1. It's related to the fact that the probability is computed using counting the number of samples to the class 1. When you are dealing with a balanced problem, you have the same number of class 1 and the same number of class 2. So if you compute the probability as a number of class 1 sample and number of class of sample of the class 2, the difference can only be related with the fact that you belong to a certain class and not to the other one. I don't know if you are seeing something about this fact.
Yes.
It's a little, because I think it's not very easy to see this fact. But the problem is that with the unbalanced problem, you will be classified to the first class, not because you really belong to this class, but because you have a lot of neighbors associated to the other class. So in this case, it's
understood
easy.
you correctly. It's a way to a different threshold is a way to compensate for the fact that we have downsampled from the class 2.
Exactly. So it's in this case, if you reduce the threshold, you are saying, okay, it's not. I don't want to have half of the first class nearest to me and half of the other class. But maybe if I have 2 samples of the second class and 8 samples of the 2 samples of the class 2 and 8 samples of the class 1, maybe 2 samples are enough to say, okay, I belongs to the class 2. Maybe 2 samples is enough in this case, because if you are maybe in the center of maybe in the center is very difficult, but you are near to the top right, maybe you have 20 sample of class 1 and only 1 sample of the class 2, and the probability that you belongs to the class 1 is higher. But in the other case, when you approach to the top right, you always have a lot of class 1 samples, but you only increase the number of samples of the class 2. So in this case, and also in this case, you can say, okay, it's not important to have a lot of samples of class 2, sorry, but to have, and I don't want the half of the one of the class 1 and half of the class 2, but I want to see some of the minority class near to me. This is the idea, and this is the difference between balanced and unbalanced.
Yeah, thank you very much.
So this is the reason, because we will change the threshold. Okay. So when we are dealing with a precision recall curve, in this case too, we can use a metric to select the best threshold, and as Han said before, we can use the F1 score. In this case, we are optimizing. We are doing 2 under 1 over precision plus 1 over recall, and we can change the threshold. Okay. And in this case, what is the goal is to optimize the precision. So if we have precision, if we optimize the precision, we are reducing 1 over the precision. We are reducing 1 over the recall. And to reduce 1 over the precision, 1 over the recall is very useful, because in this case, we will increase this ratio. And so we will try, so in the end, the goal is to increase this ratio, because if we increase to this ratio, we are saying that we have increasing the precision and the recall. So this is what this metric, this score is saying. And so in general, how to select from a practical point of view the threshold? Okay, we use a training set for learning the different models. And we select the best one using a ROC curve, a precision record curve. So a precision, we use a different AUC as you want. It depends on the problem, as you have understood. After we have you selected you selected the best model, and you have to decide what is what the threshold is. So you have to use an evaluation set. Okay. After that, you can use a test set to obtain an unbiased estimation of the error. Why we don't use evaluation set and test set together? Because otherwise we have a biased estimation of the error, because we are selecting the threshold according to the result that we want. So it's not what we want in general. It's the same as when we are doing a cross validation. We select the training, the test set, and at the end of the cross validation, we use a test set to estimate the error. And it's quite clear because in the end, the threshold, it's like an hyperparameter. So it's something that we have to select. So it's quite common to use an evaluation, a test set, whatever you want, to select this parameter. So it's the same. So we can use the evaluation, we can use an evaluation set to select the threshold. But we have to see one thing. The core model, so the model in the end, doesn't change, because it's the same model. We only change the trade-off between the sensitivity, the specificity, the precision. We are only changing these quantities. Maybe the trade-off is sometimes is better changing the changing the threshold, but the probability estimated by the model is always the same. So, and the last thing that I want to say is, if we increase, for example, the sensitivity, so the recall, we decrease the precision, and if we increase the sensitivity, we increase the false positive rates. So each time, if we change the threshold, we lose something. And so what we change is only the trade-off between the different types of errors. And so from the confusion matrix point of view, we are only moving up and down the different rows. And we are not moving, and what we want in reality is to change from the off diagonal to the diagonal. But we are not doing that. We are only changing, because why we are moving up and down the rows? Because we are changing the elements. So we are changing the label from positive to negative. So when we change from positive to negative, we are changing where our sample stays on the rows, on the first row, or on the second rows. And so we are not inducing another separation between the classes. We are only focusing differently on our sample. And so this is the reason, because usually we move on and we change, and we need something else, the sampling methods. But I don't want to talk about sampling methods today, because it's another important topic. And I think that we have seen a lot of things. So I only want to do a brief recap. So we have seen the different, what is an unbalanced problem. We have seen that is related with the frequencies of the output of the classes. We have seen that the usual algorithms have the assumption of the same number of sample, and this is related with the question. I don't remember the name of the guy's name, but it's related with the what we have said, because the KNN see the neighbors and around them and decide according to the threshold equal to 0.5. We are seeing that usually we focus using the accuracy, but it's not the best metric. And we have introduced the classical topics of classification, so confusion metrics, and how to build different metrics, so sensitivity, specificity, precision. And we have seen the difference between sensitivity and precision in particular. We have seen also that using classical algorithms can be not very useful for our problem, because we are maybe a naive model will give us will return us the same results, and we have seen that usually a metric, a ROC metric, and a precision recall metric is better to select a model. But what we don't have said is that these tools alone are not enough usually to solve the problem. Sometimes yes, it's enough, but usually we need also the sampling methods that we will see later in the next meetup. But we have seen that this is the starting point. So we start from this. You will see if you have good results, changing the threshold and selecting a model using a ROC curve and a precision recall curve. So we have seen the different metrics to select the threshold. So now we have seen also how to select splitting our sets. So now the next time we're ready to see the last part, the sampling methods. And we will see also the results associated to these sampling methods. And also how another method associated to supervised method for MLTogether classification, so the weighted loss, and this will be similar to the sampling. They will be similar to the sampling methods. Ideally, they will be ideally similar. So we will see in next meetup these last two methods. So if you have some question about what we have said today, this is the time. It's all clear.
Could you mind repeating again about I see that you said when we change the threshold, the model is not changing, right?
Yes, exactly.
Is that part I didn't really got it.
Yes,
like,
yes, it's clear.
Mm-hmm.
Because you're not changing. You have the same model, and you are changing the threshold. If you change the threshold, you're only changing the positive and the negatives. Okay? So you're moving up, and if you remember, you have on the confusion matrix, you have on the first row the predicted as positive and the predicted as negative. If you change the threshold, you change the predicted. Okay? And so you are moving up and down. If you change the threshold, sometimes you can have some positives that are that change and are predicted as negatives. Okay? Do you see it?
Okay, I got it. So like the tree or the random forest is still keeping the same, but just we change the evaluate at the end, right? That's why the confusion metric is changing, but actually the model is still the same.
Yes, it will the same. It only change from the first row to the second one, or the opposite, from the second one to the first one. But the fact is that usually you don't want your goal is not to move up and down, but to move from the off diagonal so false negative, false positive, to the diagonal, true positive and true negatives. And so you need something else, you know, that are sampling methods or other methods like weighted loss. But sometimes maybe you obtain a good result, because as you have seen, the ROC curve and precision recall curve are modeling a certain sort of a certain sort of trade-off, a trade-off between sensitivity and specificity, sensitivity and precision. And maybe if you balance these two things, you obtain enough a good result. But sometimes maybe not. Maybe it's not enough to move up and down your samples. But I think that maybe now it's a little bit clear. What do you think, Anna?
Yeah, I think it's clear. And
Okay.
I have one more question. That you told us like we will have one lectures on theory and then two section to practice, right? So next week we will try with the coding part, or we will continue with this kind of theory this presentation.
Okay, now we have two lectures on the theoretical part and two lectures about the practical parts. I don't know if maybe it's maybe it's too much to lecture. I don't know. We will see if maybe I don't know. Maybe we will do a small meetup the next time, because I don't want to do too much things together. I want to give you some part, and I don't want to do all the things that we have to do together, because maybe it's too much. But for the moment, it's important to get the idea. And after, when we will do the practical session, you will see all these concepts together. And we will spend two lectures about that.
The lecture slide today.
Sorry?
Okay. I think the lecture slide today. Is perfect.
Okay.
It's short and really concise and like very well prepared.
Exactly.
So even if next week you will do the same, then I think it's fine.
Yes, exactly.
That's in my opinion, but I don't know how about the other.
Yes, I think I will do the same thing. And for the two practical lectures, I will propose you a notebook on a problem. And this is very interesting because you can see, for example, my point of view for presenting a notebook. How maybe there are some better notebooks, but I think they are enough a good presentation. How do you present a result in general? I think it's a quite a good notebook, in my opinion. But you will establish if you agree with me.
Yeah, I totally agree.
Okay, guys, if you don't have any other questions, it's
Sorry,
enough for today.
one. Is there?
Yes.
Is there some book because the one I read don't talk about unbalanced the datasets, and they had problems with unbalanced datasets.
Yes, there are a lot of books, and okay, the bibliography will be at the end of my slides, and I will I will give you the slides, putting them on the GitHub repository of the groups. I will push them on GitHub, I think, in these days. So if you see on the meetup, you will have the link to the GitHub repository. You will have also the link to the YouTube channel if you want to see again some parts and whatever you want. But a very good book to learn unbalanced, how to deal with unbalanced problem is Applied Predictive Modeling of Max Kuhn, the main author of Caret, the machine learning package in R. And this caret is the same of scikit-learn pandas. And so I think it's one of the best book for applied machine learning in general. But you have some other good books, but you can see I have here eight source for your studies. So I will put them on GitHub in the next days. But if you want a book, what I read is applied predictive modeling.
Thank you very much.
Okay, some other questions? Thank you, Marcos. So, guys, what I can say? I can say have a nice night. Have a dinner, and bye-bye. I hope that I will see you the next Monday on this meetup. Bye-bye to everyone.
Bye, Julien.
Bye.
Thank you. Bye-bye. Bye, everyone.
Bye-bye.
Thank you. Bye.